Hello, welcome to the video. In this section, we're looking at lesson 10.1, where we're looking at lines and segments that intersect circles. So diving into some of the core concepts, uh, basically, there are a bunch of terms that we're going to have to be able to identify of these different line segments with respect to a circle. So the very first term that we're going to take a look at is a chord. All right, so a chord is a line segment whose endpoints are on the circle. So this is what they chose to represent as a chord. So any line segment where their two endpoints are on the circle ends up being a chord. Now, of that statement, you have more specific chords, and we have a diameter. All right, so a diameter is also a chord, but it is a very specific chord. All right, so this specific chord uh, means that it's a line segment that crosses through the center point of the circle. Okay. Another type of line segment that is not a chord is a radius. Radius is a line segment where it's intersected at the center and some point on the circle. If you're not aware, the radius is half the distance of its diameter. Going into lines, relationships with intersections of circles. Anytime you have a line that intersects a circle at 2 points, it is called a secant. And anytime a line um, intersects a circle at exactly 1 point, that is called a tangent line. So point B is the point of tangency in the diagram, and uh, that's where it just intersects at that 1 point. Okay. So with that, we're going to be asked, it says to tell whether the line, the ray, or line segment is best described as a radius, a chord, diameter, secant, or tangent of circle C. Okay, so the first example is AC. So AC is right here. AC is a line segment that goes from the center to some point on the circle. By that definition, it is a radius. AB, AB goes all the way across, but it also crosses the center. This is a diameter. DE, DE is right here. It appears that DE touches the circle at 1 point. So this is a tangent line. And then finally AE, which is a line here, and it's a line that intersects the circle at 2 points, so this is a secant. Other things that we're going to look at in this section is talking about, it says coplanar circles and common tangencies. So coplanar, if you recall early on in the semester, coplanar was where you had things all in the same plane. So if everything's all on the same plane, that creates an element where things can be intersected, and then we can create uh, tangencies from that. So looking at the diagram, uh, the the blue, red, and green circles, what they're talking about is different ways two circles can and interact. So for the blue one, it says you can take two circles and they can be intersected at 2 points. You could also take those same two circles and intersect them at 1 point, which in this particular case means that those two circles are tangent circles, which means that they one, you know, the smaller circle could be inside the larger one, or they could both be on the outside, both be intersected at 1 point, or you can have two circles not intersect at all. Either both circles are away from each other, or one is inside one another. It's not circle, and it's considered to be called a concentric circle. And that particular one is a circle where they share a common center point. Um, Looking at common tangents, there are two different types of tangencies. You can either have common interior tangents and common exterior tangents. Okay, so in the example, I'll explain what it means to be a common interior or a common exterior. So in examples A, B, and C, it says tell us how many common tangencies of the circle have and draw them. Use the blue to indicate external tangencies and red to indicate any internal tangencies. Okay, so the first thing you're going to look at is um, I'm going to draw a line segment between the two center points. So here, here, and here. So looking at example A, if something is, if you have a line that is tangent to those two circles and it crosses the line segment that I created, then it is considered to be an internal tangency. So for part A, there's actually going to be two internal tangencies because I can make a tangent line here and I can make a tangent line here. And because those two red lines cross uh, the black line that I created, that is telling us that it is an internal tangency. Now the external ones are still are still tangents, but they don't cross. So for part A, this would be a line of tangency, and this would be a line of tangency. So in this particular instance, they have four common tangencies. Two of them are external and two of them are internal. All right, so now looking at example B, all right, I have two external common tangencies, and I'm going to have one internal. So in this particular instance, I'm going to have three common tangencies. Now, in part C, this is where I'm going to have two externals, but I'm going to have zero internals, so that means I just have a total of two. We got a couple theorems that we're going to take a look at. The first one is tangent line to circle theorem. So if they say in a plane, a line is tangent to a circle if and only if the line is perpendicular to the radius of the circle. So here they're saying that PQ is the radius of this particular circle, and then line M is the tangent line. And if that particular line is tangent, that means that it is going to be 90 degrees to that radius. We have an external tangent congruency theorem. So if you have, it says tangent segments from a common external point, which in this case is point S, then they're saying that if you have two line segments like that that are tangent, then you can say that both SR and ST are going to be congruent. So one of the things that we're going to be asked to do is they want to know if ST right here is tangent. So in order to prove that ST is tangent with the measurements that are given, we have to figure out if this is a right angle. In order for this to be a right angle, what we have here is potentially a right triangle. So if we have all of these side measurements, we can then implement the Pythagorean theorem, the a squared plus b squared equals c squared, all right? So in this particular instance, what you were going to do is I would just use your smallest number, which is 12, is a, so it's going to be 12 squared, plus your second smallest value, which is 35, so it's going to be 35 squared, and c is going to be my largest value, which is 37, and that's going to be squared. So I want to see if this is going to be true. If this holds up true, then we could say that it has a right angle, then we could say that it is tangent. So 12 squared is 144. 35 squared is 1,225. And 37 squared is 1,369. So 1,225 plus 144 is 1369. So they both equal each other. Since they both equal each other, I can say yes, ST is tangent. Here, on the other hand, it says in the diagram, point B is a point of tangency. So they're telling you that it's a point of tangency. They want you to find the radius of circle C. So because we know that's a point of tangent, we know it's a right angle. So what we're going to do is we're still going to use the Pythagorean theorem to help us find our value for R. So like we can still use Pythagorean theorem, a squared plus b squared equals c squared. Makes it a little bit more interesting because you have R as two sides of the triangle. So in this particular instance, I'm going to say my smallest value is R, so this is going to be R squared plus the next smallest value is 80, so it's going to be 80 squared, and it's going to be equal to our hypotenuse in this case, which is the opposite side of the 90-degree angle, is going to be R plus 50 quantity squared, because you add them together. So on the left-hand side of the equal sign, I get R squared plus 80 squared, which is, what, 6,400. And then this, you have to expand it. So remember that this is R plus 50 times it by R plus 50. So you have to FOIL it out. So once you FOIL it out, it turns into R squared plus 100 R plus 2,500. Okay, so remember, you got to do that foiling out, all right, or else it's not going to come out correctly. So now, in this particular situation, if you notice I have R squares on both sides. If I just subtract R squared to both sides, they cancel. And then what I'm going to do is I'm going to take and subtract 2,500 to both sides. So 6,400 minus 2,500 is 3,900. So now I got 3,900 is equal to 100 R. Divide everything by 100. R is now going to be 39. That happens to be the radius. So my radius, knowing that point B is the point of tangency, is going to be 39. Finally, it says here that RS is tangent to circle C at S, and RT is tangent at circle C at T. They want you to find the value of X. Well, this is that external congruency theorem coming into play. So this and this are going to be the same value. So in order to find X, you're just going to take 3X plus 4 and set it equal to 28. So again, 28 minus 4 is 24. So it's 3X is equal to 24 divided by 3. X equals 8. So For that to be true, x would have to equal 8. And that is being able to look at lines and segments that intersect circles. Hope this helps. Till next time.